All right, so we're going to start with number 6 as requested, and go on to 7, and 5, and then 2, depending upon how much time we have. So in this one, we have a player passing a ball down the court. They give us the speed. The ball leaves the player's hands. Right away, when we see speed, what should we think about? What type of energy? Kinetic energy. And then they give us another speed, and they tell us that's at its highest point. When we hear height, we should think about potential energy, gravity. Excellent. All right. And then they tell us ignoring air resistance. So to me, that triggers, there's no external work on this. And because it's a changing situation, I know that I'm going to be using my energy bar graphs. And as you guys said while reading it, KE and PE grav are the two columns that I'm going to use. I don't think there's anything else going on there. So let's see. When we're going to go from when it leaves the person's hand, the player's hand, till it's at its highest point. All right. So our initial condition will be leaving the player's hand. Our final system energy will be at its highest point. All right. Let's call where it leaves the player's hand a gravitational potential of 0. All right. So we've got this type situation. Here's our player. They've got the ball. They throw it. It's up here, and we're going to call this height 0. Therefore, this is h. Right? Everyone picture situation? Yeah, let's call that 0. So at the beginning, it's going to have a bunch of kinetic energy because it's moving and it has inertia. Because we're calling that point the 0 point, it has no gravitational potential energy. There's no. How do I know there's no external work done? It says ignore air resistance, and there's no friction or other obvious things like a bird attached itself to the ball and added energy to it or something. Oh, you laugh. That could be a death problem.
Oh.
Roger throws a basketball and a seagull swoops down and grabs it in its talons. Web feet. You want me to use you for that one, Ellen?
Yeah, I know.
I'll think about that. I'll write myself a note. All right, let me write myself a note. Ellen bird ball problem.
Yeah. I'll make it the easiest one. You make it the bonus point.
All right. And then, so is it going to have more or less kinetic energy at the top? Less. And let's say a bunch less.
Much lesser kinetic energy.
And that extra energy went into its gravitational potential energy.
Would it have a higher potential?
Not necessarily.
Could it?
It could, yeah. Remember, what's the important things here, this graph? Or the essential things? That you represent all the energies, and that initial plus during equals final.
So I wouldn't be wrong if I had a no.
Nope. You might even be more correct. You want me to change mine to match that?
No, it's wrong.
You sure?
No, I was just wondering.
Good question. All right, so right away, that leads me to my how. It says that the kinetic energy initial has to equal the kinetic energy final plus potential energy, gravitation final. The bar graphs give us the equations. Really kind of essential understanding
There's no
that.
word.
Huh?
Okay.
So let's see, now I have to remember, what do they want to know? They want to know what height it ends up at. Okay. Well, let's see. This is 1/2 mv speed initial squared. This is 1/2 mv final squared plus mg. Where am I getting all these weird letters from? Where are the G's? That's a 2. Weird 2. Otherwise known as our equation sheet. Let's see. Oh, now it's just filling in numbers, right?
There's
It is. Any algebra you can do on that real quick? Algebra?
M dots.
The V's do not cancel because, remember, to cancel something, it has to be in every term.
the M.
So the M's cancel. Is there a 1/2 in every term?
No.
No. Could we get rid of the 1/2? What would we have to do? Multiply everything by 2. That would get rid of them. But you can't just cancel them out. You can just cancel out the M's, though. Right? Because those have to be in every term. And then just solve for H. And I know you guys can do algebra and arithmetic, so I won't bore you by doing it. Let's start number 7 here. Very similar to that, one of the example problems. I think we got to it, I'm not sure, but it varies by class. I think it was example problem number 3.
I think we skipped full measure though.
Pretty sure we skipped 3? Oh yeah, well, you know, it happens. So, they want to know about the gravitational potential energy when the bob reaches A, the speed of the bob at point A. Oh, the speed of the bob at point A. Oh, good. And they tell us all this about point B, has the mass of this, and is moving. Oh, it's moving, it must have kinetic energy. Is it moving at point A? Possible, right? Not quite. I'm hoping it does. Otherwise, well, we could test, right? How could we know if it's actually moving at point B? At point. Oh, they don't even ask us if it's moving at point A. They just say moving at point B, right? Okay. Oh, what is the speed at point A? Yes. So we could test and see if it was moving at point A. You can put in a 0 for part B, and if you get it correct, yay, it wasn't moving. But I doubt they would ask the question if it wasn't moving, right? Hello? Moving on.
Wait,
So, yes, I'm listening.
I thought you were moving on to the question.
No, I am moving on from trying to get you to do that. So I'm going to use the same 2 columns I used last time. Do we think there's any external work being done here? No, I'm gonna assume that there isn't. Oh, air resistance is negligible. That tells me there, right there, right? And because there is an Ellen bird coming in here. Oh. All right. You're imagining Ellen as a bird?
Yeah.
All right, so this will be at point B, is it? Yeah. Our initial will be at point B, and then our final will be at point A. So at point B, lot of kinetic energy. At point A, less kinetic energy and more potential energy, gravitation, than it had before. What assumption did I make? Janet, what assumption did I make? All right, so we've got our bar graphs, and of course those immediately translate into an equation that says KE initial equals KE final plus PE G. Now, let's not use final and initial. Let's use B and A, since those points are named for us, right? Maybe it makes it easier to make correlations. And they want to know the system's gravitational potential when Bob reaches point A. And we know it's 35 degrees, but they don't tell us what height this gets up to. So I think I need a little picture to help me. There's point B, there's point A. Goes up a height h here, right? And can we call the length of the string L? Is that okay with everyone? Okay. And does everyone understand that the string would be the same length when it's at point A as when it's at point B? Yes?
Yes.
Okay. And so we could make a right triangle here, right?
Oh. Yeah.
And then, this side of the right triangle would be L cosine 35 degrees. And this side would be H. And that length would be H. I know, a little geometry here. You gotta take back that when you said your geometry teacher. When will I ever use this? You gotta go tell them. I found it, there was a time I had to use it. So L equals H plus L cosine 35 degrees. Huh? That's a good question. Which measurement out of all this do we need? Which do we have? We need H. Do we have L? Do they tell us how long the string is? Yep, 1.2 meters. So I'm going to rearrange this and say so that I have H equals L minus L cosine 35 degrees. Yes. So we can find H, and they want to know how much gravitational potential energy it is gained. Part A, right? Maybe I should switch to blue. Well, we know that PE grav at A is going to be M, G, and H. Do we know M, G, and H? Yeah, now we do. We didn't before. We didn't know H before, but we knew M and G. And then B, they want to know how fast it's going. So you're going to use our equation that we found there from our graph. And your knowledge of kinetic energy being 1/2 speed is v squared. Thank you. Right? Oh, look, you have that value. Always happy when you can reuse the value. And then you know m. You know the speed at b. Why do we know the speed at b? Because they give it to you. And I know m. And hopefully I know 1/2. And I'm looking for VA. Now, I'll tell you the most common mistake people will make is that they will just say, okay, I'm going to substitute all that in, and I'm going to get VA equals, and then they're going to be, I got the wrong answer. And the common mistake is they forgot the square root. So what I suggest is put in all your values, solve for VA squared, and then physically write that down, and then below that, write VA. It's more work, but it's less likely that you will forget to square root it if you have to write VA squared equals and then VA equals. Do with it as you will. Questions on this one before we move on to another? Yeah. Newtons per kilogram. Why is G 9.81 newtons per kilogram? Because we're assuming this takes place on the Earth. Now, if I said, hey, they're swinging the pendulum on the moon, it'd be like 1/6 or something. You'd look on the equation sheet and find the value for it, or it'd be given to you or something, or you might have to solve for it. Yeah, it's close to 1/6, if not exact. All right, so we're going to go on to number 5 here. That was the next one requested. Some people struggled with this one yesterday when I was doing it in A block. Not because of the physics or the math or anything. Maybe it was first block. They were having a hard time because they weren't reading all the words in the problem. Where it says, like down here, that you're putting in 3 answers. You're putting in the KE, comma, the PE graph, comma, the total energy. All right? So, be careful of that. All right. So that was what they struggled with. You know, they were putting in one number and going, I'm getting it wrong. Well, you have to put in all 3. So, we have an apple falling from the tree to the ground. Right? So I'm going to go rather quickly because so we'll do the first column at the top of the tree. Why can I assume the apple wasn't moving at the top of the tree?
Because there's that lion. Oh, that's top of the tree. So the apple off the tree, right? So it's not moving.
That's a good reason. Yeah. Any external work done on the apple as it falls?
No.
No. How can I tell that?
Ignore air resistance.
Ignore air resistance. And our bird isn't there, so. It says to take the bottom of the tree as 0, but it doesn't want to know this at 0, it wants to know it at 3. Right? So, like, here's our tree, happy little tree. Apple, yeah, Roger. Apple starts here. That's at 4 meters. They say this is 0, but they want to know After it's fallen 3 meters? No, when its height above the ground is 3 meters. So they want to know at this point, which is 3 meters high. So has it fallen very far? No. So which one do you think it'll have more of? Kinetic energy or potential energy graph?
More potential.
More potential, I would say.
But it's still. Oh,
Yeah.
There's more. Okay.
More potential graph than kinetic. What if we did this but it was only at 1 meter?
Like 4 to 1. There'd be more kinetic because it's almost heavier.
Yeah, a lot more kinetic than potential graph.
Wait, look at 5.
Oh, look, an equation again.
Oh.
Graph initial at the top of the tree equals KE. Oh wait, why don't we use 4 there? It's at 4 meters, right? KE3 plus PE G3. Now, one thing that people miss, each of these is equal to the total energy, right? So when it asks for the total energy, yeah, quite a lunch. So when they're asking for KE and PE grav at 3, those are going to add up to the total energy. So if the 3 numbers you put in, first 2 don't add up to the third, should you submit? No. So let's see. What do we know? Do we know M? Yeah. Do we know G?
Yes.
How do we know what little g is?
For assuming this happens on Earth.
Because we're on Earth, so it's 9.81 newtons per kilogram. Okay. Oh, so we can do this one, right? We can find that one. KE3. I'm going to leave that one. Oops, I've got my parentheses here. H3. Oh, wait a minute. I can find all that. I can find KE3, couldn't I? Because I know M, I know G, I know. What's H4? What's the value of it? 4 meters. What's H3? 3 meters. Yay! And then once I know KE3 and PE4, can I find PE3? Yay, because that's the other answer they want, right? And then, add those up and I get the energy total. Yay!